Hello everyone and welcome back to Particles in a Box. Today we are going to be doing episode number 6, Forces, Dynamics, and Statics. So this is going to be a pretty big episode. There's going to be a lot covered within the span of this episode. And so I don't want to waste too much time. I just want to get into it. We got a lot to cover, and this might be a multi-part series of episodes. There might be more than one episode for the problems because there's a lot of interesting problems and a lot of important results that can allow you to shortcut future problems in like future episodes by getting the base problem done in this episode. So there's going to be a lot of examples, there's going to be a lot of problems, and there's going to be a lot of theory. So without further ado, let's get into it. So first up, force is a vector. So if you go back to our kinematics episode, right, we talked about scalars, we talked about vectors, right? So force is a vector. And if you remember correctly, that just means that it has some sort of magnitude and direction. And that because of that, you can divide your vector up into an x component and a y component. And you can also have a magnitude and an angle, okay? So we're going to be making full use of that in this episode to help us in our problems. Something that isn't necessarily a review, but we're going to be dealing with what are called inertial reference frames. Okay, and inertial reference frames, all that means is that the observer is not accelerating. Okay, that is important because if you are accelerating with respect to whatever is going on, that can make your problem much more complicated. And we'll talk about that at some point. That might be a very long ways down the road. But for now, to keep things simple, we're going to be dealing with inertial reference frames. So you can be stationary, you can be moving at a constant velocity, but you can just not be accelerating. We're also going to be dealing with Newtonian mechanics, okay? You know, if there's one episode where it's all about Newton, this is pretty much that episode. So what that means is that we're not traveling at relativistic speeds. We're not traveling at large fractions of the speed of light. We are moving at what we would call quote unquote slow speeds. Okay. So that's just an important disclaimer to always mention. So there's also different types of forces. Okay. So the main four forces, if you're familiar with more of quantum physics or just like reading about physics, you'll know, but some of you might not know. There are four fundamental forces that govern everything that happens in the universe. Okay, those are gravity, the electromagnetic force, the strong nuclear force, and the weak nuclear force. Okay, and we're not really going to be talking about any of these in this episode. Gravity, we'll briefly mention gravity, but we'll be doing a full episode dedicated to Newtonian gravity in the future. And then the rest of these forces are for way farther down the road. But what we will be talking about today is contact forces, okay? And so what do I mean by contact force? It's just when two things are touching each other, that is a contact force. And so examples of contact forces are friction. So when you like rub, when things are sliding with each other, that's friction. The normal force, which we'll get into and we'll talk about what that is. And then resistance forces. Technically, these you could say are frictional forces, but I kind of like to put them in their own separate category. And so these include like internal forces inside of a spring that gradually prevent the spring from stretching, also called a damping force. Air resistance is an example of a resistive force. And then like tension in a rope would be an example. We're going to be talking a lot about tension in today's episode as well. So Newton's laws of motion. Some of you are probably familiar with Newton's laws of motion. Some of you might not be. So the first law, right? There are multiple ways to state this, and some of them are objectively more correct than others. So let's take a look at a few statements and see what the first law entails. So first up, we have an object in motion will stay in motion unless acted upon by an outside force. Short, simple, pretty straight to the point. The second one, an object will continue at its current velocity unless acted upon by an outside force. So the key difference here is that we have a mention of velocity, right? And that's a key part of Newton's first law. Then we go to the third statement. If an object does not interact with other objects, it is possible to identify a reference frame in which the object has zero acceleration. I'm not a huge fan of this one, especially when I'm like teaching physics to like newer people in physics and less experienced people, because again, the idea, like the word reference frame is pretty vague most of the time, and it can mean a lot of different things to a lot of different people. And yeah, it's not super intuitive what this is actually trying to tell you. If we go to the fourth statement, in the absence of external forces and when viewed from an inertial reference frame, an object at rest remains at rest and an object in motion continues in motion with a constant velocity. So this is perhaps maybe the most complete statement. But all these are trying to get at the same concept, right? Is that if an object is moving, unless there is a force that acts upon that object, it is going to keep moving in the same direction with the same velocity, okay? Or the same speed. If you apply a force, right, then the direction or the magnitude of the speed and therefore the velocity is going to change, okay? So this is the conceptual way to describe the first law. Like, is there a mathematical description? And the answer is yes, there is a mathematical description. So what the first law is trying to get at is this concept of inertia. Okay, it's the tendency to resist a change in velocity. Okay, and so inertia is equal to the mass. For our purposes, inertia is just straight up equal to the mass. And so to mathematically describe this, right, the best way to me to describe this, right, is with this equation, okay? The force is equal to the time derivative of the momentum, okay? Now, some of you are going to be like, well, where's F equals ma? Don't worry, we're going to get there. Don't worry, it's coming. It's just that we haven't talked about momentum yet. So for some of you, you might be like, oh, what's going on here? The key idea here is that there is a velocity in this, right? So when we're talking about changes in velocity, right, you have a velocity to talk about, right? And there's also a mass here, right? So that's our inertia component, okay? So that is one definition of the force. We'll get to F equals ma in a moment. And we'll talk a little more about this form as well. But when you're talking about Newton's first law, this is a good form to use. It mathematically enhances the concept and statements that you're trying to talk about. Okay, so second law of motion. Okay, here we go. So F equals ma, okay? So there's sort of two different ways in which you can state this, right? Is that if you have a singular force acting upon an object, right, that force is equal to the mass times the acceleration, times that singular acceleration, okay? But in the problems that we're going to be doing, there's going to be more than one force acting upon these objects. And so you take a sum of all the forces that are acting on the object, so a net force, right? And that's going to be equal to the mass times a net acceleration, okay? So you can have multiple different forces, and when you add them all up, you'll get a net acceleration out of it, okay? And it is important to mention that the mass times the acceleration, right, is that theoretically, there could be a proportionality constant here, okay? There could be some k here, right? But experiments have determined that the proportionality constant is 1, and that is with quite incredible precision as well. The universe would be definitely a very different place if the proportionality constant was at 1. So yeah, we'll just state that, and we'll go to the next slide. So the next thing we got to talk about is inertial and gravitational mass. Okay. You might, at first glance, you might be thinking, what? Inertial gravity? What is going on? So there's a force that we're familiar with, gravity, right? The force of gravity is equal to the mass times the acceleration due to gravity. And we dealt with the acceleration due to gravity in our projectile motion and kinematics episodes. But then there's also just like the generic force, right? Just a mass times any acceleration, right? And And this gets at the concept of weight versus mass, okay? This right here is a weight. This is a mass, okay? So the box is the weight, and the circle is a mass. Most people are pretty familiar with this, and that weight and mass are two different things. But it's always a good idea just to rehash that to make sure everybody's on the same page and that there's not any misconceptions flying around. Okay. But it turns out that the inertial mass and the gravitational mass are equal to each other. Okay. So in the previous slide, right, we talked about that I mentioned that proportionality constant, right? There is, right, the proportionality constant is 1. There is no difference between a gravitational mass and an inertial mass. Okay. When you do relativity, this is not necessarily the same, sort of, because you're dealing with energies as well. But in this episode, the masses are equal, and this has been experimentally determined through experiment. Again, to remarkable precision, we can discern no noticeable difference between a gravitational mass and an inertial mass. So let's get into a quick example here. A hockey puck with mass of 0.5 kilograms has 2 forces acting on it. One force is 10 newtons at 40 degrees, and another force is 3 newtons at -7 degrees. What is the net force on the object and the net acceleration? So how we do this is that you can just draw a generic object, okay? Forces are going to act from the center of mass, okay? We'll talk about center of mass in a future episode, but to keep things simple, forces are going to be acting from the center of mass. And so if we like have some sort of coordinate axes, right, like 40 degrees like out here, right, and then -7 is something like out here, right, and then the magnitudes of these, right, are 10 newtons and -3 newtons. Okay, so as review, right, if you want to add these two, you want to break them up into components. So we're going to have our x component, so you got 10. The cosine, right, is the horizontal components. The x component plus 3 times cosine -7 gives you like 10.63 newtons. And then you can do y, which is the sine of the angle that you're using, gives you about 6.7 newtons, right? And so then if you wanted to find the magnitude of the resultant force, right, you're gonna add them in quadrature. You're gonna get about 12.62 newtons, and then you can take the arctangent of your y over x component, and that gives you about 32.5 degrees, okay? And then if you want to find the acceleration, right, we know that F is equal to ma, so you can take our net force divided by the mass, and that gives us a quite large acceleration of 25.24. So this object is moving quite rapidly, very quickly. So that's just a quick review of how we can add multiple vectors on an object. Okay, so I've now brought up F is equal to ma and F is equal to this change in momentum. Okay, so it's important to kind of recognize why there's two different forms, how these are actually the same, and when is it useful to use one or the other. Okay. So the first question is the mass constant? Okay. In F equals ma, the mass right here is constant. Okay. The mass of your object is not changing. When you use the momentum one, you can have a derivative with respect to time of the mass. Okay. When does this happen? The most common example is a rocket. You are throwing fuel and mass out the back of your rocket to propel you forward. That is a change in momentum because you're losing mass. And that is also a force as well. So when we talk about momentum, we'll talk more about rockets and the rocket equation and how that works. But for right now, that is one example of where the mass isn't constant, and you would need to take that into consideration. So the context of the problem is also very important, right? The momentum definition is very useful in relativity and quantum mechanics, where, again, our masses are not necessarily constant, and momentum and energies are more well-defined in quantum systems. It's easier to deal with energies and momentum than forces directly, so that's why the momentum can also be used. It also matters, is the force constant? In this episode, the forces are going to be constant, but that might not always be true. And so you might have to like find an average acceleration or an average velocity, or you're going to have to do some sort of integration or something to find your force at a particular time, or find the average force, or you're going to need some other mathematical tool just besides a straight up one of these equations to figure out what's going on. In this episode, we're going to be dealing with F equals ma. The momentum one we'll talk about farther down the road. It's just important to mention here. And yeah, so we'll be using F equals ma to keep things simple. So now we're on to Newton's third law, okay? So one statement of Newton's third law is every reaction has an equal and opposite reaction. So if two objects interact, the force F1, or in other words, the force exerted by object 1 onto object 2, is equal in magnitude and opposite in direction to the force F2, the force exerted by object 2 on object 1. So the best way to describe this, right, is if you have two boxes right next to each other, right, and you apply a force from this first box onto the second box, right? That's force F1. There's going to be a force back on the box that is opposite in direction but equal in magnitude. This is not always true, it turns out. It's one of these statements where laws are not always true. And so let's talk about that. So yeah, it's simple in concept, but unintuitive in application. And there'll be an example after this that's also going to highlight that. It's true of most contact forces. I struggle to say all contact forces, but for most contact forces that we're going to be dealing with mostly contact forces when we do our problems and examples in this episode. But Newton's third law is true of central forces. And what a central force is a force that acts along the displacement between two objects. Okay. So if you have, again, the two boxes, right, and we're applying a force, right, our box isn't moving, but we're trying to go in the same direction as our force is applied. And so the force is acting along what the displacement would be. So examples of this are the electric force and gravity. And yeah, we'll talk more about, again, when we talk about gravity, you'll have a better picture of this, but just know that central forces, Newton's third law does work. When it doesn't work is for velocity dependent forces. Some forces, like spring dampening, air resistance, the magnetic force, they have a velocity component to them where you can write down an equation that has the force as dependent directly on the velocity, not necessarily the acceleration. And Newton's third law does not hold true for those. There's more going on than what can be described there. In the next episode, we're going to be talking about, in the next major episode, in episode 7, we'll be talking about air resistance, and you'll see an example of what a velocity-dependent force looks like. But for now, central forces obey Newton's third law. Velocity-dependent forces do not obey Newton's third law. So there have been some proposed additional laws, and I kind of like to use laws quite sparingly in that, well, again, right, these might only be true in Newtonian physics. They're not necessarily true when you take relativity into account. So, you always got to take that with you always got to evaluate that. So the first one is that the sum of a big mass is the sum of the individual masses, right? So if you got a big ball, right, you have to take into account that it's the sum of all the atoms and electrons and all that stuff in there. It seems intuitive, but yeah, I mean, okay, yeah, I guess that makes sense. Forces act instantaneously. This is a big one, right? If you go out into the scientific media, right, and you start reading about like gravitational waves, for example, right? Gravitational waves are relativistic. That's why they take time to act. But Newton, one of his consequences of his equations and laws is that forces act instantaneously. So that's also imposed as a quote unquote law, even though it's not really actually how the universe works. And then also a proposed one is forces change the energy of an object. We haven't talked about energy yet. Yeah, this is true. I threw up the energy equation, but you have an individual force times the displacement. If you integrate that, you get the change in energy. Again, we'll talk about energy in the future. So yeah. So an example. So before we do this problem, I'm gonna throw up a bait warning. Okay, remember I said it's simple in concept but unintuitive in application. This problem is gonna highlight that. Okay. So a book is sitting on a table. The Earth exerts a force on the book by Newton's third law. Which of the following is the correct reaction force? So we just have a book that is sitting on some sort of table. Okay. Right? And so the Earth exerts a force. That force is the gravitational force that just points straight down. Okay. So which of the following is the correct reaction force according to Newton's third law? Okay. Because there needs to be a force in the opposite direction that is equal in magnitude. Okay. But which of the following adequately describes this force? The table exerts a force on the book. So the table exerting a force on the book. Okay. That seems plausible, right? I mean, the book doesn't fall through the table, right? So there's got to be some sort of force from the table, right? The book exerts a force on the Earth, or the book exerts a force on the table. Okay. So because I specifically mentioned the Earth in the problem, right? The correct answer is actually number 2. The book exerts a force on the Earth. And so if you're new to physics and you're thinking about this, you're like, how can the book possibly exerting a force on the Earth? And the answer is, well, it does. First of all, the reason why you probably don't think it exerts a force on the Earth is because the Earth doesn't move, right? Like if you just drop the book, say the table wasn't there, right? The book is going to fall to the ground, right? But the Earth doesn't move towards the book, right? I mean, that seems crazy. Well, the answer is that the Earth does move a little bit. I mean, we're talking on the orders of like 10 to the negative 24th here is like the value of the acceleration that the Earth experiences as a result of the book. It's even less than that. Okay, so it's not even really measurable, to be honest. But okay, so then you might be thinking, okay, so the book exerts a force on the Earth, but how does the book not fall through the table? There must be a force that the table exerts, right? And the answer is there is a force. There is a force that the table does exert on the book. And that force is called the normal force, okay? So the normal force is a contact force, and it just acts perpendicular to a surface, okay? So if we put our box back up here, and we have our table, right? There is a force of gravity, right? But the table itself pushes back up on the book, right? So that the book doesn't fall straight through, okay? And so, again, right, we have a force downwards on the table, and then the table is exerting an equal force back up, right? So this gets into the concept of how do you define your system and, what exactly is happening in the problem and whatnot. Needless to say, as a result of what I described to you in these 2 slides, right, the force that these blocks and tables exert on the Earth is neglected. We don't care about that because the Earth isn't going to move any quantifiable amount, but we do care about the forces that are interacting between the blocks and the tables and the blocks of each other, right? We do care about those because there is enough of an acceleration that is measurable and that is big enough so where we can actually observe something interesting. So yeah, keep that in mind. So then next up we have the frictional force. So this is due to contact between surfaces that act in the opposite direction of the net displacement, right? So if you have a block, right, and you're moving that way, the frictional force is in the opposite direction of your displacement. Okay, so the force of friction is going to be in the opposite direction. Okay. Key things to note here, right, is that it is mostly independent of the surface area. We say mostly because in most real life applications, there is some dependence on the surface area, right? Big examples of this are like tires on the road, at like racing type tires. The surface area does have an effect on the friction. So do keep that in mind. The other thing is that we're not dealing with any sort of thermal or energy or heat loss as a result of friction, right? Like if you rub your hands together, right, or you've seen those like wooden like drills, right, where you can like start fires, right? That's the frictional force creating a lot of heat. We are not going to be discussing that in this episode, so keep that in mind. So how the frictional force works mathematically is that there are two different types of friction. There is static friction and there is kinetic friction. Okay. So static friction. Let's talk about kinetic friction first. So kinetic friction occurs when the object is moving. The velocity of the object is not zero. Okay. And that is equal to this coefficient. This is called the coefficient of kinetic friction. Okay, denoted mu k. Times n, where n is the normal force. Okay. So the normal force that we just talked about, right? The frictional force is directly proportional to the normal force and multiplied by some constant. Okay, and this constant depends on the surfaces that are being rubbed together, and you can look, and you'll just be looking up this value most of the time, unless the problem is asking for you to solve for it. I mean, it depends on if it's aluminum and copper, if it's wood and steel, right? It depends on what materials you're using. But then there's also static friction. So static friction occurs when you are not moving. Your velocity is zero, okay? And so this force is less than or equal to the coefficient of static friction times the normal force, okay? So these two coefficients are different. Mu s is almost always greater than mu k. I tried to look up an example of when this wasn't true and I couldn't find one. So, but all the textbooks I've ever read have said almost always. So let me know in the comments if you know of an exception, because I'd be interested to find out about it. So the deal with this, right, is that when you're stationary, right, you're going to start pulling, right, and you're going to keep pulling, and eventually you're going to apply enough force to get the object to move, right? So this force of static friction needs to scale up until you reach a threshold, at which point the object starts to move, right? So that's why there's this like less than or equal to sign, right? Is that the force of this force scales from 0 to this value, right? And once you apply this value of force to the object will start moving, okay? And then once the object starts moving, right, you can actually apply less force than to keep it moving, which is really interesting, right? So that's why it's like if you're struggling like move an object, right, and then like a really heavy object, maybe like a couch or something, right, and you're pulling, eventually it moves, right, and then you kind of have this like jerk reaction where like you kind of like lose your footing or whatever, right, because there's all of a sudden like a rapid change in acceleration now, because all of a sudden you go to kinetic friction, which has a lower value than the force you applied. So now you need to quickly apply less force, right, to keep it from like flying over the top of you. So that's where like a real world example kind of comes into play. So some notes on problem solving. So we're going to be going through a bunch of problems here. The problem solving process is pretty similar for all these problems, right? So we'll kind of walk through that real quick, kind of what the generic steps are. And then it's just after that, once you kind of have the general steps, right, it's just cranking out and getting as much practice on these as you can so that you just kind of build up that intuition, build up some practice, and see how the math works. There's not really a better way to describe that. It's just one of these things where having experience doing it, right, and kind of recognizing, oh yeah, right, I need to remember that. I can't forget this factor. I can't forget this force, right? That's just something that you build up over time. So the first thing is that what is the difference between statics and dynamics, right? On the title slide, I said forces, statics, and dynamics. Okay, so if the sum of the forces on the object are 0, then you're dealing with statics. Okay, it's not necessarily to say that your object isn't moving per se. That would also be statics. But if your net force is 0 and you're just moving at constant velocity, that is statics. But if the sum of the I misspelled that. That's my bad. But if the sum of the forces is not 0, then you're dealing with dynamics. You have a net acceleration, and your object velocity is going to be changing. That's called dynamics. So you go from statics to dynamics by applying an extra force that is not balanced out by your other forces. So how do we go about these problems? The first thing, right, is you're going to read some sort of word problem, okay? It's going to give you a description of what's going on. Some problems, if you're lucky, might give you a picture, but if there isn't a picture provided, you're going to want to draw one, okay? And this, what we're going to be drawing is called a free body diagram. So, for example, right, you'll read a problem. We do a lot of boxes because they're simple. And then based on what the problem is telling you, you want to label each force, right? So is there an applied force in some direction? Is there a normal force? Is there a frictional force? Is there a gravitational force? Is there some other force, right? Is there multiple applied forces, right? You want to draw all of those on each object, okay? And if you got more than one object, then you have to draw, forces on each object. Breaking up the forces into components may be helpful. In fact, it most often will be. So yeah, keep that in mind. You want to make sure also that when you're drawing this picture, right, you define your axes, right? So that's y, that's x, that's positive x, and that's positive y, right? There might be situations where it's beneficial to draw them like this, right, where positive y is actually downwards. There are situations where that can be useful. So making sure that you define your axes properly can save you quite a bit of hassle. There are multiple instances where you could quickly be led down a rabbit hole or quickly led in the wrong direction if you don't label your axes properly. Then you want to set up your equations, and then you want to solve for your desired force or acceleration. So one common question that they'll ask you, right, is it wants you to find the acceleration of the object. And then they'll take it like one step farther where they'll ask for like, oh, what is the final velocity of the object? What is the final position, right? And so you can kind of shortcut this, right? And that once you find the acceleration, you can go back to our kinematics episode, shameless plug, and you can apply the equations of kinematics assuming that the acceleration was constant, right? So if the acceleration is constant, you can go back to kinematics, you can plug in your velocities, your accelerations, your displacements, and solve for whatever one of those that you need, okay? The other thing here, right, is that we're not going to be dealing with these in this episode, but sometimes you'll be given like a graph, right, of something. And so like you might have a graph of like velocity versus time, right? And it could be some weird function, right? And you might be asked to maybe discern something about the force or the acceleration, right? So it's this is just a reminder to, okay, velocity versus time. You can find the acceleration from this, right? You can take the derivative. That gives you the acceleration, right? Then if you multiply the acceleration by a mass, you can get the force, right? Now the force obviously in this example is changing over time, but you now at least you can get a force graph from this, right? Same thing goes with momentum, right? If you take the derivative of the momentum with respect to time, you now have a force. Okay, right? That's good. And then and then acceleration versus time, right, is if you just multiply that by the mass, right, you have a force, right? So just reminding yourself that, hey, I'm maybe not given a force directly, I may be given a graph. You can still find information related to forces based on the graph that you're given. Okay, so now we're going to go on to some examples, and we're going to see how we can apply what we've just discussed in a more practical manner and see where in doing these problems there might be some things to watch out for and how you can, approach these yourself. So first question, the blocks are connected by strings. Imagine you pull the front block. What are the relative tensions in the strings? Now you stop the blocks. What are the relative tensions in the strings? Okay. So I kind of already have a little bit of a photo here, right? I've just laid out some blocks, right? We're going to call this block 1, block 2, block 3, and block 4. Okay. And we're going to apply a force straight out of the front. Okay. What are the tensions in these strings, right? So this is a conceptual question, right? And you might kind of be thinking, okay, so each of these ropes, right, has some sort of tension in them, right? Your initial reaction might be to say that they're all equal. I wouldn't blame you for saying that, but unfortunately that is not true. The key thing to think about here, right, is that you apply this force, and so this is going to have some sort of acceleration, right? And this first rope, right, has to pull block 2, 3, and 4. So that's a lot of mass that you're pulling, right? But this one here, right, well, you're only pulling the mass of 3 and 4, right? So the acceleration for all of these is the same, but the mass that each string is pulling is decreasing as you go backwards, as you go back, right? So this one has the greatest, and then that one, and then that one, okay? So one has the highest tension because you are pulling the most mass with the same acceleration. Then the second one, you have a little bit less mass, but again, still the same acceleration. And then the third one, the least mass with the same acceleration. Now, if I apply my force in the opposite direction, it's still the same deal, right? You're still applying an acceleration here to a ton of mass over here, but back here at the very back, right, you're applying a force on less mass at the same acceleration, okay? So this is just to show, remember, just kind of slow it down, right? Sometimes your initial reaction is not always the right one, contrary to what people tell you sometimes. So just kind of a nice conceptual question to get us started off with. So our second example. As always, you're welcome to do these examples by yourself if you want to try them out first. Otherwise, you can just follow along if you want. You can pause the video and then unpause it. Do whatever you see fit. A box hangs from a system of 2 strings, which are massless. Find the tension in each of the strings. So this is the first sort of example of where we are saying that things are massless. The reason why we do this is that it simplifies the problem. And it actually is a pretty decent approximation, right? Like if you're using like fishing line, for example, like that doesn't have a whole lot of mass, right? The problem is that if it's not massless, you technically have to take into account that the string has mass and that the force is, distributed over the whole length of the string, and that the string is in some respects a spring that like stretches, right? We don't want to deal with that, right? That's beyond the scope of this video. And most of the time, assuming that these strings are massless is actually a pretty good approximation. So it kind of works out. Okay, so all of a sudden you probably see this block of math come up. It's like, oh my gosh, what's going on? Again, let's break it down and see what's going on, right? So over here on the right, we have a picture, right? The first thing that we want to do is we want to label this as theta 1 and label that angle as theta 2. Okay. And then we want to draw the forces, right? So we have a force on the block pointing straight downwards. That's our gravitational force. Okay. And then we have 2 other forces, right? We have the force from the second string and the force from the first string. Okay. So those are our 3 forces that are acting on this block. Okay. So from Newton's second law, right, we can write that force is equal to mass times acceleration, and we're specifically going to break this down into components. Okay. So we're going to use the x. So we have an equation for the x components and an equation for the y components. So for the x components, right, we're going to label our axes like this, right? We got a positive y up here, and a positive x over here. And so what this allows us to do, right, is that we can now use the horizontal components of our tension in our two strings and set them equal to 0. Okay, right? So this string here has some horizontal component. This string over here has some horizontal component. Okay, and you have these angles here, which are these angles, by the way, just so you know, and that works. And you set them equal to 0, right? This block isn't moving in the x direction, so there's no acceleration, so there's no net force. Okay, there's no net acceleration or net force. And then we're going to do the same for the y. Okay, so this time we're going to be using the vertical components, and this time we have gravity. Okay, so the total force from these strings pulling upwards needs to be equal to the gravitational force downwards. Otherwise, the block is going to move. Okay. Yeah. So we don't want the block to move. So the upwards force needs to equal the downwards force. Okay. So we want to find the tension in each of the strings. And so what we want to do is we want to eliminate a variable. Okay. So we got 2 variables and 2 equations. So that's good. We got the same number of variables as we do equations. So we can just do a direct substitution here. So we're going to solve for T1. Okay. The important part to recognize about this is that there's this negative sign right here, right? What that is telling us is that the force from one of the strings is in the opposite direction as the other string. So for the x equation, right, one string pulls to the left in the x direction and one string pulls to the right in the x direction. Okay, so it's a good thing that we have that minus sign there. Once you find your T1, right, you're going to plug that back into your equation up there. And you're going to get this down here, right? And then we're just going to go through some algebraic simplification. Down here, right, you're going to use a trigonomic additive / subtractive identity to simplify this into a sine of theta 2 minus sine of theta 1, right? And then you can algebraically solve and you can get the tension in the second string. And then you can take that result, plug it back in up here, and you can get the tension in the first string. The important part to recognize here, right, is that you want to be you got to be careful with your minus signs. Like up here, right, I could have initially just said that put a minus sign there initially, right? My philosophy is it makes sense for me to just kind of leave everything positive, right? If I leave everything positive, the signs should work themselves out. And it's also the case of, well, you can find a magnitude of a force and then describe its direction later, right? So you can say, okay, well, I know that the magnitude of these two need to be the same, but they're in opposite directions, right? And so, right, so when you go from T2 to T1, right, the reason why there's no negative sign here, right, is because, well, you switch the direction of your subtraction. And so that works out pretty nice. The other thing here, right, is that just a reminder that T2 does not equal T1. I see a lot of people make this mistake. The x components are the same, but the y components are not. Okay, I'm going to say that again. The x components are the same, but the y components are not. Okay. So one of these strings is going to have more force on it than the others. Okay. That's kind of a fun bonus problem if you want to tell me which in the comments below which one of these strings actually has the greater force. But keep that in mind. Don't fall into the trap. And this is a pretty good example of a typical problem, right? You have some forces acting on something, and it's going to ask you to find one or multiple forces. So next problem. A car is on an icily frictionless driveway at an angle theta. Find the acceleration of the car. So at an angle theta, don't want to add there. So sometimes in these problems, right, they'll directly say that something's frictionless. Sometimes they'll kind of hint at it by some indirect language. So do make sure you read the problem carefully. That's just a kind of a heads up and a warning. Okay, so we have our block here, which we're gonna use as our car, right? This is an angle theta, okay? And we're gonna do something a little bit interesting, right? So the normal force acts perpendicular to the surface, right? So gravity is gonna act straight down, but our normal force is gonna be off at a little bit of an angle, okay? And so what we do to make the problem easier here, right, is that this is some angle theta, but it is the same angle as down here, right? We're just tilting our axis the same amount to make sure that this normal force is perpendicular. But what we want to do is we want to tilt our axes, okay? So that the x direction is parallel to the ramp, okay? And then the y is perpendicular to the ramp, okay? So we want to do that, right? And so as a result of tilting the axes, right, you have this angle theta as well here from our gravitational force, okay? And so as a result of tilting these axes, we now have components to our gravitational force, okay? So we're gonna let Fn be its own thing. We're not gonna break Fn into components. We're gonna break gravity into components, okay? Now if you're wondering why would we do that? Why not make the normal force into components? When you start dealing with friction on these problems, it makes it a little bit easier. So the part that you want to watch out for, right, is since the angle is right here, your horizontal component is a sine, by the way. I see so I'm gonna throw up a bait warning. They're throwing it up. This is a common mistake. It is a sine horizontal component when you do this. It's the opposite. It's not the adjacent, it is the opposite here. So when you're doing your x component, make sure that you plug in the sine. That's a common thing that I see. And so in the y direction now, right, we have the normal force minus the gravitational force. Again, you could have left this plus, but I know the gravitational force is going to be in the opposite direction. There is no net force in the y direction, so it's going to be equal to 0, right? The block doesn't go through the ramp. So we want to keep that in mind. And we also, in the x direction though, the force is just gravity times the sine of theta. So like we said, the acceleration in the y direction is 0, but we do have a net acceleration in the x direction down the ramp. And so when you solve this for ax, right, you're going to get g sine theta. Okay. Making sure that you remember that mg is equal to fg, and that is the answer, right? So you also can check to make sure, okay, does this make sense? Yes, right? If I plug in sine of 0, right, so it's flat, the block isn't going to move. If I plug in sine of 90 degrees, the sine part becomes 1, and you're just left with g, and the object is just falling, okay? So that makes sense. That checks out. That seems reasonable and somewhat intuitive. So our next problem, a block is pushed with a horizontal force into block 2. The surface of sliding is frictionless. Find the acceleration of the system and find the magnitude of the contact force. So what we got going on here is we got two blocks. We got block 1 and we got block 2. Okay. And so let's go ahead and label our forces, right? So there's no friction, so we want to keep that in mind. Drawing it on our block here, right? We got gravity downwards. We have the normal force upwards, and we have an applied force. Okay. Block 2, we also have gravitational force. We have a force upwards, and we have a force from this block. Okay. So F of 1 onto block 2. Okay. Well, we missed a force, right? We have a contact force here, So block 1 also has a force backwards, okay? So this is our applied force F, and then this is our contact force of the second block on the first block, okay? So the y directions, they're all going to cancel out. There's no net acceleration in the y direction, right? Nothing's falling through the table, okay? So what we got going on here, right, is that for the system, right, we have the total mass times the acceleration of both blocks. We're treating this as though they're together. And so we have our applied force plus the force over here minus the reverse force, okay? Well, again, F21 and F12 are equal and opposite, right? So when you subtract those two, you're just going to be left with F, the net force. And so then you want to expand out your total mass, right? Just the sum of the masses is equal to F. And so the acceleration of the extraction is F over the sum of your masses. Okay, that's pretty cool. And so then if you want to find find this contact force, right, you can just apply the sum of the forces onto the second block only, instead of the entire system. And so you can use this result and plug it in here, right? The acceleration of the second block has to be the same as the same system acceleration, right, for the dystopian contact, is equal to F is equal to the contact force. And so when you solve through and expand out your mass, right, you get that, right? So yeah, that checks out, right? Now, for some of you keen observers, you might be like, well, will these two blocks actually stay in contact? Well, that's a bonus problem for you to figure out. So if you want a challenge problem, you can go ahead and think about that and let me know what you come up with in the comments. So a box is on a scale in the elevator. Determine the reading of the scale when the elevator is accelerating in the vertical direction. Okay, so we have our box, which is an elevator. Okay, it is accelerating in some direction. It could be accelerating upwards, it could be accelerating downwards, it doesn't matter. Okay, we have a block on a scale, right? So we're going to have a normal force upwards, and we're going to have this gravitational force downwards. Okay. And so you have an acceleration of the elevator, right? And the key part about this problem is that all the elevator and the objects inside are all accelerating at the same rate, okay? The objects inside are accelerating at the same rate, right? If they weren't, then the block would like fly off the scale and things would be flying around inside the elevator, right? So everything is accelerating at the same rate for everything to be stationary. Well, stationary, right? Stationary in quotes, right? And so we know that Fn minus mg needs to be equal to the mass times the acceleration of the elevator, right? And mass is referring to the mass of the block, right? By the way, not the mass of the scale or the elevator. Okay, we don't know anything about the mass of the scale or the elevator. We just know something about the mass of the block. And so the scale measures the normal force. It does not measure the gravitational. It measures the normal force, right? And so that's the other key part about this problem is that the normal force is not equal to the gravitational force in this problem, right? Yeah, let that sink in for a minute, okay? Right? Scales measure the normal force. They don't measure gravity, actually. So keep that in mind. That definitely throws people for a loop. So if you solve for the normal force, that should be a capital N. You get the mass times the acceleration plus g, right? And so if you take a look at this, right? If the acceleration is less than 0 and the elevator is going downwards, right? The normal force is less than the force of gravity. Okay. I'm plugging in g here as positive, by the way, just so you know. So then when you plug in a negative acceleration, right, you're going to get closer to 0, and you are going to have a normal force that is less than the value of gravity. Okay, so that's why when you're going down an elevator, right, it can feel like you're like a little bit like weightless. Well, not weightless, right, in sort of like the space sense, but like it feels like you're lighter, right, because you're accelerating downwards. But if the acceleration is greater than 0, right, aka the acceleration is upwards in the elevator, then you're gonna feel a little bit heavier. There's gonna be a little bit more normal force, and you're gonna feel a little bit heavier, and the scale's gonna read higher. So next problem. 2 blocks are hung vertically over a frictionless and massless pulley and string. Find the acceleration of the system as it is released from rest and the tension in the string. Okay. So the first things first is that this setup is called an Atwood machine. Okay. We'll be doing we'll be revisiting this a couple of times here, right? If you remember in the problem here, it has that the pulley is massless and frictionless. As we move forward in episodes, we're going to start removing restrictions on these pulleys and these strings, right? We're going to say, you know what, the string actually maybe has mass, right? It isn't frictionless, right? And so we're going to start, gradually whittling away at that. But for now, we're going to do the base case here: no friction, massless string, massless pulley, the whole bang. So let's label our forces, right? We have a force upwards and we have a force downwards, right? So we have the force of gravity. Okay, that is the worst FG I've ever written. We got FG, and we have our tension force, okay? And then over here we also have, and this is F of G1, by the way, and this is F of G2. These forces are not necessarily the same, as our masses are not necessarily the same either. But the tension is the same, right? This is the same string, so the tension in the string is always the same. The other thing that you got to realize is that the positive direction sort of changes, right? It's a curve positive direction. This isn't super easy to explain. I'm just going to use the excuse that the math works. It adequately describes what goes on and matches experiment. So yeah, it works. And so as a result of this, right, the force of gravity is negative on the first block. The tension is positive on the first block. The second block, because we then go across the curve, the tension is now negative, and the gravitational force is now positive. Okay. That's nice because tensions are now eliminated. Okay. And so you can go through and solve for the net acceleration, right? Keep in mind, this is a system of 2 masses, so you got to add the masses together, and you can find the net acceleration of the system. This is an important result. You don't necessarily need to memorize this per se, but it does come up frequently. You're going to see a lot of things in this form. So yeah, I think it's an important result to show. And then if you want to find the tension in the string, right, the best way to do this, right, is to, okay, we're just going to take the first block. We have the tension minus the gravitational force. We now know A, right, from up here. So you just can go ahead, plug that in, and you can solve for the force. And by doing some algebraic manipulation, finding your common denominators to add your fractions, right, you get you get 2m1 m2g over m1 plus m2, which again is also an important result. You're going to see in problems similar forms to this as well. So the reason why I mentioned these, right, is that if you get something in this form, right, you can maybe be like, okay, I've seen this before. That's plausible. That seems like it could possibly be a right answer. Okay, if you're getting weird things where you're like adding extra terms and stuff, then maybe that can be a little bit of a warning sign, like, hey, maybe I did something wrong here. Let's see. So we got our next problem here. I think we got a couple more examples. One block hangs off a table while the other block sits on the table. The blocks are connected by a string over a pulley. The pulley and string are massless, while the table and pulley are both frictionless. Find the acceleration of the system and the tension in the string. So pretty similar problem here compared to the last one, right? Except we have our second block staying on a table. So we have our forces, right? Right. So we'll do that, right? We have our normal force, we have our gravitational force, we have the tension force, and that's Fg2, by the way. Then we have our tensional force, and we have our gravitational force. Okay. Again, this time I went like this for our positive direction. And we can ignore the normal force and the gravity on block 2. It's frictionless, so there's no extra force we got to deal with, right? We're just caring about the tension and the gravity here. So it's a pretty similar process compared to the last problem, right? Except the tensions here in this first equation are going to cancel out, and there's no extra gravitational force we have to deal with. There's only one gravitational force, so there's no m2g. And so then once you find that acceleration, you can plug it into block 2, and you can find the tension in the string, which again, right, matches the form, right? If you remember from the previous slide, there was a coefficient of 2 here. That coefficient just isn't there this time, but it's of the same form, right? You have the two masses multiplied by each other times g over the sum, right? So, okay, that seems plausible, right? That makes sense. So let's see, I believe this is our last example. A hockey puck is given an initial speed v. The puck goes a distance d. What is the coefficient of kinetic friction? So we're going to do a quick friction example here. When we do problems, we're going to deal a lot more with friction. I just sit here when we're doing the examples, right? It makes sense. Okay, we'll just do the examples without friction, and then in the problems, we'll put it in. So this is a pretty boxed hockey puck, but you know, it's going to work. So we have our forces here. Oh, okay. Oh, sorry for that. So we have our normal force, our gravitational force, and our frictional force. Okay. The displacement is that direction. Okay. So the net force in the x direction, right? We are going to take x positive to be that way and y positive to be that way. Is just equal to frictional force. Okay. But it's important that you still label your normal force and your gravitational force, because the frictional force is dependent on the normal force, right? So you want to make sure that you have that in there, right? And when you're doing these problems for the first time, right, it might be helpful to write the sum of the forces in the y direction is equal to the normal force, which is equal to the gravitational force, which is equal to 0. Okay, right? That just explicitly states that your normal force and your gravitational force are the same, right? Because you're going to want to plug in mg for the normal force here in this problem, right? That isn't necessarily always going to be true. Fn is not necessarily always going to equal mg, right? We saw the ramp problem, right? And that wasn't true. But, you know, sometimes, right, right, I understand, okay, right, the normal force is equal mg, right? But as somebody who's new, who's doing this for the first time, right, writing things out explicitly, writing out every single detail can be a little more important. So I want to make sure I mention that. And so your masses, if you deal with one puck, are going to cancel out, and you find your acceleration. Okay. And so then our acceleration is constant. Okay. We have a constant force of friction. And so we can use our kinematic equation here to solve for the coefficient of kinetic friction. You get your mu k here. When you solve for it, you get a v squared over 2g delta d. So this is one way that you can semi-quickly figure out the coefficient of kinetic friction of an object, right? Is that if you know the velocity at which you release the release the object, you can then measure the distance that it goes, and you can find the coefficient of kinetic friction that way between whatever surface you slid it on. There are other ways to do that. We'll when we do problems, you'll see that there's more than one way to figure out the coefficient of kinetic friction, and yeah, well, that's in the problem episode. So with that is going to be the end of the theory and example part of forces, dynamics, and statics. As always, feel free to like, comment, subscribe. There were a couple of possible thought experiments and things that I said, if you want to give them a try, go ahead. If you ever want to, check your answer or have a discussion with me, feel free to send me an email, or you can leave a comment. And so until next time, have a great day, and I will see you in the next episode.